This is Mary Montgomery for assignment 6. Looking at part 1, question 1, we're adding normals to everything. So for our model tools, the only thing I changed was adding a helper function for my normalized pyramid sides, for normalizing the sides of the pyramid. Model tools.cpp, we'll go through this quickly. We just added normals to all our models. So for the box, it's pretty easy. It's just whatever way the face is pointing. Unit box repeated texture, same thing. Unit box 6 face texture. Adding normals, so the normals are aligned to whatever axis is perpendicular to the face of the vertex. For forward, our normals are pointing perpendicular out of our forward face, which points directly forward along positive z. For right, points negative x, etc. So it's the same for all the boxes. We just had to duplicate vertices. Create unit pyramid. So we needed to duplicate the vertices for the differing normals. The vertex normal is equal to the normal of the face, which is found using the 3 vertices of the face. I have my normalized pyramid sides function, which we can look at. So to find the normal, I send in the 0th point, which is always the top of the triangle, the first and the second, which are the bottom sides in the counterclockwise winding order. And then we set the normals, the x, y, and z of all the normals. Same with repeated texture, same thing. And so our normalized pyramid sides takes in the vertices of the face of the pyramid, computes the 2 vectors that lie on the triangle edges, which are my u and v, and then calculates the face normal with u cross v, divided by the magnitude of u cross v, where magnitude is found with this math, but in reality, we can just use the dot norm function. So that was for all my model tool normals. For terrain, I added 2 helper functions for the find vert norm and calc trinorm, which we will look at in here. So the only thing I changed within my terrain model.cpp class, everything's still the same. I just have this calculate normals function now. And since we have that normal.set function, we can set the normals after creating the verts in the vertex buffer. So I didn't change anything with my vertex buffer or my index buffer. I just added this little loop. We can also ignore the edges and therefore edge cases and just calculate the normals of the vertices that have 6 triangle faces touching it. And I use the helper method find vert norm. So we go through all of the inner, the field vertices, I believe they were called, the inner vertices, and then find vert norm calculates the normal of the vert, accounting for the 6 connected tri faces. So we have our list of vertices, the vertice we are currently on, and then the length of side. And then we set the normal of that vertice. So looking at that function, find vert norm is down here. So I kind of had to draw it out for myself. We have a visual of the first 3 rows, and then programmatically I figured out how they would be found, and then I just wrote it out in actual code. It's each triangle, add those triangles normals together to find the vert normal, then normalize it. And so within this normalization, I have this calc trinorm helper function, which is just up here. It calculates the individual triangle's norm based on the side vectors, which is what we did for the pyramid in the model tools class. All those normals are added together and then normalized, and then we return that. So that is how I found the terrain normal. And then putting that all together, I have my pyramid and box model and terrain created in dxapp.h, and then in dxapp.cpp, we add the new models, pyramid, box, terrain, add our new world matrices. Then we, in our draw function, draw scene, we're using the already set to context p shader color light shader, and we're just sending the world a material. Our pyramid is fire brick red, we're setting it to context rendering. Our box is teal, and then our terrain is salmon. And let's see what these all look like, reflecting the light. There they are. I'm not great at moving the camera, but you can see the light's being reflected off the terrain, the pyramid, and the box. Looking at part 1, question 2, create a new shader class that combines the ability to apply a texture to a model and incorporates lighting. So here we're looking at our HLSL file, colored light texture.hLSL. It combines the color light and the texture HLSL files to create color light texture. So it's basically the color light HLSL file, but we needed to add our texture and sampler. Everything else is the same. The other change was to, in our VS output struct, we needed to add our texture coordinates for the UV. And then we need to include that in the parameter of our VS function, or vertex shader function. So now we have the texture in there, and we have to set the texture, the output texture, to the texture in the parameter. And then in our pixel shader, the last thing we need to change was just at this very bottom. We needed to account for the texture color in the final color. So we found what each pixel is going to be lit with, the lit color, but we needed to render out our sampler, our texture, also with that pixel with the lit color on top. Looking at our shader color light texture class, our header, this shader is almost identical to the shader color light shader. This one just accounts for texture through our set texture resource and sampler method. So that's the only change we have in here is our set texture resource and sampler method. It's our texture specific method. It's implemented in the .cpp file. The other changes we had to make are small. I messed up with this for a while though. Make sure we're correcting the correct HLSL file in this constructor. Make sure we're coloring our new color light texture HLSL. We also have to update the input layout to include position, our new text coordinates, and the normal, and make sure our offsets are correct. And then just our new set texture resource and sampler takes in texture as a parameter, and it calls our texture classes set to context method to set our texture to context. Looking at dxapp.h, just making sure we added our shader color light texture new class pointer. And in dxapp.cpp, we are using our new shader color light texture shader. We create it new. We are setting the point directional and spotlights in draw so we can switch shaders and also set the shader to context in the draw stage. We're preloading the models and textures here. And then in draw scene, we are setting our new P shader color light texture to context and setting the spot directional and point light parameters here. And then sending the cam matrices and eye position to the shader where we set our light parameters as well. Then we render out our shapes, one on top of another, add the textures to the shader before rendering it out. We don't need to set the textures to context. That's done all through the texture class, which is called through our set texture resource and sampler method that we just wrote. All of my models are being set with the material just color white so we can more easily see the texture. Then we set the model to context, render it out. We do that with our pyramid, our box, and then our terrain, each with their own texture. And then I switch back to the shader color light shader just for the flat planes and that circling box so we can go textureless for those. But here's that all rendered out. And there are my textured pyramid, box, and terrain, all reflecting the light. Looking at part 1, question 3, creating a scene with multiple lights, creating an HLSL shader and associated shader class that will allow me to have multiple lights in my scene. So looking at our new HLSL, texture multi-light, it's a copy of my color light texture HLSL, but just with added functionality of light arrays. It's pretty much exactly the same. The only changes are in the light parameters constant buffer. We need to update the point and spotlights to be arrays. Right now I have them as arrays of size 3. And then the only other change is in the pixel shader. We need to loop through our arrays now. Instead of just computing the point light of our single point light and computing the spotlight of our single spotlight, we loop through the array of point lights and the array of spotlights. And then it's the same, returning the texture and the lighting at each pixel. Looking at the shader classes, our shader texture multilight.h file, the shader is almost identical to my shader color light texture shader. It just has some constant buffer light differences. So let's see. So in our point light struct, we needed to create a point light data array of 3. And for spotlights, it's the same thing, create a spotlight data array of size 3. And then in our data light params struct, we need to create arrays of point lights and spotlights, both of size 3. Then implemented in the CPP, first we need to make sure we are setting the correct shader base HLSL file, our texture multilight new HLSL file. Make sure the input layout matches. And then the changes were in our set point light params. We added an index parameter so we can set the point light params to 1 light at a time. And that same change was made in the set spotlight params. We have an index parameter so we can set the correct spotlight. And then in our send light parameters, we have to account for each of the array lights. So since we have 3 of each, we are manually setting those to our passed in point and spotlights. So looking at dxapp.h, we just added our new texture multilight shader, as well as a few other things we'll need. And then in our dxapp.cpp file, in the init, we are creating our new shader texture multilight shader. We set the point direction on spotlights and draw so we can switch shaders, also set the shader to context in the draw stage yet again. All we need for this demo is the terrain. So we have the texture of the terrain, which I'm using the sand grass, the terrain, which uses my height map, and then the world of where that terrain is, and then positions for the spotlights. In our draw scene, we are setting the new P shader text multilight to context and setting the directional light and the multiple point and spotlight parameters. So for each of these, I just set 2 and 2 since I only need 3 lights. So we're setting it to context, set directional light, and then setting spotlight parameters in the 0th index and the 1st index, and setting point light parameters, 0th index and the 1st index of those respective spot and point light arrays. Setting the cam matrices and eye position to the shader and setting the light parameters, which will update our arrays, spot and point arrays. And then we're just rendering out the terrain, setting the world and material, making it light so we can see the texture better, and rendering it. So let's see what that looks like. We have our 2 spotlights and 2 point lights that we will see. And there they are. These are our 2 spotlights and our 2 point lights.
Looking at further work question 1, tune shading based on the exercise in the textbook. So all I really needed to change, I copied over my code from question 1, just the regular color light shader file. So within our fawn model is where we set the diffuse and specular computations. So to implement the tune shader, we changed the diffuse and specular computation by discrete functions to make them stepped values rather than interpolated, which is done through helper functions I created. So with this diffuse float 4 we found, we step the diffuse x, y, and z values with our tune shader diffuse function, and we do the same for the specular tune shader spec function based on this spec that we found here, that float 4. So let's look at our helper functions, which are just above. Our tune shade diffuse creates diffusion through steps rather than interpolation. So if any of the diffuse x, y, or z values are less than or equal to 0, they're set to 0.1. If they're less than or equal to 5, they're set to 0.3. If they're less than or equal to 1, they're set to 0.7, which is done, and then we just return that diffuse value that we created based on these if-else statements. And then our tune shade specular is the same thing. If the specular is less, x, y, or z is less than or equal to 0.1, sets to 0.0. If it's less than 0.8, sets to 0.4. If it's less than or equal to 1, we set it to 0.8. And that is the only change we really had to make. When we run our code, we will see a bit of tune shading. If we back up now, we can see the color differentiation is no longer interpolated. It's more solid. We can see what's being lit and what's in the shadows. So yeah, that is a little bit of a basic tune shader.